All right, welcome back. So this is part B, solutions of differential equations. We are primarily interested in linearly independent functions, or more to the point, linearly independent solutions of a linear differential equations. Now, actually, always we can use the definition that we have just studied in the previous video. If you are just, for example, let's say we are dealing with a differential equation, and in our hand we have a bunch of functions. And how do we determine that these functions are linearly dependent or independent? And why should we determine this? If some functions, actually, if this set is linearly dependent, it means that some functions, maybe one or more, we don't have to keep them in that solution, because those functions can be represented as a linear function of the others. So actually we need to find a set of functions where they are linearly independent. That's how we describe the solution of a differential equation in a very compact way. One way to determine this, actually, if you are given, let's say this f1, f2, fn possesses at least n minus 1 derivatives. All right. That means that at least n minus 1 times we can differentiate these functions. Okay. Then the determinants. That's equals, here we have in the first row f1, f2, fn. In the second row we have the first order derivatives of these functions, and in the nth row it is n minus 1's order derivatives of these functions. Okay, where the primacy node derivatives is called the Wronskian of the functions. Okay, so this is how we define the Wronskian determinants. And it's really important to determine if these functions are linearly dependent or independent. This is another way of determining a bunch of functions, either they are linearly dependent or independent. Theorem. Criterion for linearly independent solutions. Let's y1 or y sub 1, y sub 2, y sub n, and here we are given n functions, be n solutions of the homogeneous linear nth order differential equation 6 on the interval I. Then the set of solutions is linearly independent on I if and only if, this is if and only if, Wronskian determinant is not equal to 0 for every x in the interval. And this if and only if means these functions are linearly independent if is not equal to 0. If this determinant is not equal to 0, then these functions are linearly independent. Okay. Definition: fundamental set of solutions. Any set y1, y sub 1, y sub 2, and the dot 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 y sub n of n linearly independent solutions of the homogeneous linear nth order differential equation 6 on an interval I is said to be a fundamental set of solutions on the interval. Okay. This fundamental means if you just find any solution, all right, any solution, that means that can be expressed as a linear combination of these functions. Okay, they describe, actually they're like building blocks of the house. All right, so this y sub 1, y sub 2, y sub n, a linear combination of these functions produces all possible solutions of the differential equation, because we know that the differential equation 6, it may have infinitely many solutions, right? Now we will see them in example. Existence of a fundamental set. There exists a fundamental set of solutions for the homogeneous linear nth order differential equation 6 on an interval I. So because before we start solving that equation, we may think, actually, okay, we are starting, but are we sure that we will get the solution or not? Actually, the equation 6, the equation 6, that is homogeneous differential equation, it has always have a fundamental set of solutions. In this theorem, it's about general solution. And okay, after finding this fundamental set of solutions, how do we write the general solution of the homogeneous equation? Let's y sub 1, y sub 2, dot, 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 y sub n be a fundamental set of solutions of the homogeneous linear nth order differential equation 6 on an interval I. Then the general solution of the equation on the interval is C1 times y sub 1 with C2 times y2 blah 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 Cn times y sub m. So that means that these linear combinations of these functions produces all possible solutions of the homogeneous equation given in 6. Example. Let's say y1 equals e to the power 3x and y2 equals e to the power minus 3x are both solutions of the homogeneous equation y double prime minus 9y equals 0 on the interval. And you may wonder, okay, how did I solve this? We haven't studied how to solve this equation yet. Okay, first we are going here, we are trying to be familiar with these basic concepts, definitions, and theorems. And using these definitions, we will start solving these equations. So by inspection, the solutions are linearly independent on the x-axis. Because if you are only two functions, how do you know that these two functions are linearly independent? Okay, that means that at least one of them should be different from 0, right? For them to be linearly independent. C1 times F1 plus C2 times F2 is equal to 0. Okay, now assume that this C2 is not equal to 0. If I assume that C2 is not equal to 0, then here, because here I'm assuming that this F1 and F2, these functions are linearly dependent. Okay. If linear dependent, that means that we are able to find C1 and C2, at least one of them is not equal to 0, so that the linear combination produces 0 here. So here, if C2 is not equal to 0, from here take it to the left hand side, and I can describe this F2 in terms of this F1, right? That's equal to minus C1 over C2 times F1, okay? And I can just label this thing with K or C, or maybe just C, okay? Then this F2 is equal to C times F1. Okay, if you're talking about two functions, if they are linearly dependent, then we should be able to write one function as a constant multiple of another function. But is it possible if you multiply this function by any constant number, it's never equal to e to the power minus 3x? Or if you multiply this function by any constant number, it's never equal to e to the power 3x. That means that these two functions are linearly independent. Okay, but now another way, for example, how I can determine that these functions are, linearly independent. So if you just evaluate this determinant e to the power 3x, right? E to the power negative 3x. But here, if you differentiate this, here we have y prime, 3 times e to the power 3x. If you differentiate this, here we have minus 3 times e to the power 3x, right? If you evaluate this, determinant is equal to negative 6, which is not equal to 0. That means that this set is linearly independent. That means that actually it forms fundamental set of solutions of this differential equation. So to write the general solution, just all linear combination of these two functions give us the general solution of this differential equation. So all of the linear combinations, we just write it as y equals c1 times e to the power 3x plus c2 times e to the power minus 3x, right? So that is the general solution of the equation given on the given interval. Okay, and here I'm assuming that you know how to evaluate determinant of 3 by 3 matrix or 2 by 2 matrix. Here, how we are evaluating this, Wronskian here, you are given something like this. Let me just write here A, B, C, D, right? It's just equal to A times D, all right, minus B times C, okay? And 3 by 3, we'll see later. Example 8, a solution obtained from a general solution. The function y equals 4 times sin of 3x minus 5 times e to the power minus 3x is a solution of the differential equation in example 7. maybe we are talking about this example. Okay, y double prime minus 9y, y double prime minus 9y is equal to 0. It says that this also a solution. Okay, but here you may think that, okay, we are just saying that here this c sub 1 times e sub power 3x plus c sub 2 times e sub power negative 3x is a general solution. But here, is it possible to write this one as a linear combination of this e sub power 3x and e sub power 3 negative 3x, right? Actually, by just doing some algebraic manipulation, using this linear combination, we can obtain this solution. For example, here we have 4 times e to the power 3x minus e to the power minus 3x, because of this definition, right, is equal to this. Or here, C2, we are taking this C1 as 2 and C2 as negative 7. And if you just substitute here, and C1 equals 2, right? And C2 equals negative 7, and evaluate this, we will get this function. And what is e to the power 3x minus e to the power minus 3x over 2 is equal to sin of 3x. Another way is also here y equals 4 sin 3x minus 5 times e to the power minus 3x, right? Equals 4 times. What is this sin of 3x? It is defined as e to the power 3x minus e to the power minus 3x over 2. Right? It's just compact, or say notation for this, nothing else. Minus 5 times e to the power minus 3x equals 4 times 2 is 2. So here we have 2 times e to the power 3x, right? And here we have 2 times this, and this one is negative 5, negative 2. So here we have negative 7 times e to the power minus 3x. Okay, as you see here, it's just here. This one is C1, and this one is C2. And also this thing is just the linear combination of e to the power 3x and e to the power minus 3x. All right. So you should not get confused that, okay, this is a solution, but is it possible? If this is one of the solutions of the given equation, this equation, then we are sure that it is just a linear combination of these two functions. Okay. General solutions, solution of a homogeneous DE. One more example, the functions y1 equals e to the power x and y2 equals e to the power 2x and y3 equals e to the power 3x. Satisfy the third order equation, y double triple prime minus 6 double prime plus 11y prime minus 6y equals 0. And we are not going to verify here, and we are just accepting that it's true, because if you substitute this thing, it must satisfy this equation, and also this e to the power 2x, it satisfies this equation, and e to the power 3x also satisfies this equation. Okay, now if we evaluate it is determinants, here we have y1, y2, y3, y1, y2, y3, y1 prime, y2 prime, y3 prime, y1 triple prime, double prime, y2 double prime, and y3 double prime, right? And if you just evaluate this, determinant is equal to 2 times 6 to the power, e to the power 6x, and which is never equal to 0, right? For every real value of x. Then the functions y1, y2, and y3 form a fundamental set of solutions of this differential equation on the given interval. Then the general solution of this equation is just a linear combination of these things. Okay, guys, this is determinants, okay, in the quiz or midterm. And in a short time, how do we evaluate the 3x3 determinants? And most probably I'm going to ask a similar question. Okay, you need to practice a few determinants and calculate them, especially 3x3. And here, to evaluate this determinant in a fast way, let me use this notation. Let's say t is equal to e to the power x. Then our determinants will be, what is it? Here we have t, and here we have t squared, and here we have t cubed. How about here? We have t, here we have t, here we have 2t squared and 4t squared. Here we have 3t cubed and 9t cubed. Okay. Now, in a determinant, actually, either from a row or from a column, we can just take a common factor out. Okay. In the first column, what is a common factor? It is t. And if I just take t out, here 1, 1, 1 left. In the second column, t squared is a common factor. So here we have t squared. The third column, t cubed is a common factor. The inside, what is left here? We have 1, 1, 1, 1, 2, 4, 1, 3, 9. So here we have 1, 1, 1, 1, 2, 4, 1, 3, 9. Okay. And also, if you just subtract one row from another row, the value of the determinant does not change. Okay, so here we have t to the power 6. As you see here, we have e to the power 6x. It comes from here. 1, 1, 1. Let me multiply the first row by -1 and add to the second row. So here we have 0, here we have 1, here we have 2. And multiply by -1 added to the third row. Here we have 0, here we have 3, and here we have 8. And if I just evaluate this using the first column, this 1 times this determinant, right? So it is 8 times 1, 8 minus 3 times 2, it is 6 is equal to 2. So this thing is equal to 2 t to the power 6. And what is t? 6. What is t? E to the power x. So that's equal to 2 times e to the power 6x. Okay. That's all. Thank you.